Hi everybody. We all know the bandwidth growth is most intense in hyperscale data centers. The migration to 400 gig solutions is now underway, and even faster speeds are on the horizon. That's why co-packaged optics and onboard optics are such an interesting topic. I recently had the chance to speak with Hamid Arabzadeh, the CEO of Ranovus, a hot startup out of Ottawa that has developed a quantum dot laser technology. Earlier this year, they introduced a silicon photonics device that scales from 800 gig to 3.2 terabits per second in a single device. They've also formed an alliance with IBM and TE Connectivity and Senko to build an ecosystem around this technology. Here's our conversation.
When I look at our core technology, when we started in 2012 in the company, we started with a new concept on a laser. You know, a laser is a key part of any application, be it module or co-packaged optics. Light source today is can generate one of these wavelengths at a time from a chip. So if you want to have an 8 wavelength system, you have to have 8 laser chips coupled 8 times into silicon photonics, you know, low yield. There's a lot of different things that happen here. So we started with a quantum dot laser in 2012, which is a gain medium and material science that based on physics, it generates multiple wavelengths simultaneously from a single chip. I'm not sure if you're familiar with this, but this is almost like is a holy grail for optical networking. If you have a single chip and you can generate many wavelengths simultaneously.
And are other people using the same quantum dot?
People have developed quantum dot, you know, for lower bit rate applications because it's very hard to keep the noise of these. There's about 30 million dots, which are about 10 atom in size, on a 250 micron chip, and these are built. They're self-assembled dots based on quantum mechanics of how this is fabricated. There's no let's say lithographic or or any type of thing to create these dots. They're self-assembling. So you have to have the environment, the conditions, and the IP to know how much material, how to apply it, and all that. So people have had success with quantum dots for sensors at a gigabit per second, maybe 5 wavelengths for those type of application, but nobody had been able to reduce the noise of these dots to the quantum dot lasers so that they could modulate at a high bit rate. Okay. So we're the only company, and we've Telcordia qualified this. This is not some science experiment for DARPA or something like that. This is really, you know, qualified, Telcordia qualified, temperature range, you know, all the aspects of it.
And are there thermal characteristics of quantum dots an improvement?
Absolutely. So they can run at much higher temperatures, which is a very important element. You know, today's modules are based on EML technology at, let's say, 400 gigabit, the ones who are not silicon photonics based, and they are very temperature sensitive. So if you want to build an 800 gig module, then it's very unlikely that you have very low yields with that lasers. And DFB lasers have a certain temperature range, but the quantum dots can operate at very high temperature. They're actually more efficient at higher temperatures. So you can have the laser more closer to the switch chips and other things without having it have any degradation in its performance. So that's the source of light. Imagine now you can create a source of light that is a single chip and can generate many wavelengths. Then we started to looking at the second holy grail, which is a ring resonators. These are modulators. They're demux modulator and a mux function. So imagine if the laser is putting all these wavelengths in different colors. Each rings in a 20-25 micron space in silicon photonics can select a specific wavelength and modulate it using our driver, because we design our own drivers and TIAs as well, and then put it back into the stream. So you have it in a very small footprint, and this is a really key element. There's absolutely, I don't think anybody has come forward for co-packaged optics using anything but ring. They are all proposing the same type of architecture. I mean, I think because the beachfront of these rings, if you were to compare it, let's say, if you were to compare, let's say, the silicon photonics for rings versus Mach senders, which what Intel is using, Luxtera is using, these are their commercial products that they're using. You can see the difference in size is enormous. 20 micron versus 2.6 millimeter. The picojoule per bit is 10x lower than Mach sender. and there's other attributes there. So as you can see, the size of it matches almost the copper pillar size for ASICs. So if you have a beachfront on the ASIC that has a lot of compact SerDes beside it, the ring could match that beachfront. So you don't have to fan out from the chip to go into something bigger that you would have to do for Mach-Zehnder. Now, when we started on the rings, of course, we started patenting some. We have some foundational patents in rings. They are type of, it's like developing film in a camera, like Polaroid had. Okay, something of that nature, which we've been granted globally in US, in China, in Europe, and so forth. And so the other people who were, and we've been building on that patent portfolio extensively on rings. So we're very comfortable that anybody who would want to use a ring, we would have a very, very good case if they want to commercialize it. Of course, for tests and ARPA and all these are okay, but we would be. We have a very strong patent portfolio which we've developed since 2012 in the rings. So if you think about co-packaged optics, and it has to be rings. Now, even I saw Intel's announcement, they're using rings for their co-package solution, which I think was a system they had built based on discrete components. They said that they're using rings in there, and it's great because that sort of gives more validation to this architecture, which we've been working on for the past 8 years.
How about that manufacturability, though?
Yeah, so we have also qualified Telcordia qualified our rings. We have our first product, which already has all of these functionalities in it. And right now, there used to be, silicon photonics used to be a boutique industry about 5-6 years ago, with some boutique foundries attached to universities and other things, and they still exist. But tier one players now have come into the space, tier one foundries. So we have already validated all of this in those foundries. So we're fairly. I mean, we have a whole bunch of patents on the control loops around the rings because they're very temperature sensitive. And also around the manufacturability that we've demonstrated through our Telcordia testing.
Okay.
So if you look at these two foundations, and then I mentioned the laser, that's a very, very important element of this. You have to have it's a system. It's a complete system, starting from laser to silicon photonics to high-speed electronics to link design from SerDes, and you have to have that understanding of the entire system to be able to innovate in different parts. And then you do patents that go between each of the junctions. So you have an interdependency patents and things of that nature, which so we have our own foundry, proprietary foundry that we build our own lasers, quantum dot and quantum well lasers, and these help us gain a better understanding on how to solve the problems. Now, just to accelerate to go to your question about modules and CPO, so about 3 years ago we started looking at this picture whereby taking our technology, which was miniaturized, qualified into the data centers, and we found the logos you see here are all the major players that that we have. I can't talk about our relationship with each of these now because you're recording this, but it's really looking at the module space for 400, 800 gig and co-package optics in this space. And as we were developing the technologies in this area, we got pulled into chip-to-chip connectivity. Because our platform is protocol agnostic, and I'll share that with you in a moment. If you look at the chip-to-chip space or even networking space, you've seen the NVIDIA Mellanox. These are the moves that have already been made in the market, and you can see the optical connectivity is a major part of that of those activities there. And you look at this is from a OCP from Facebook. You can see GPUs connected together for a scale-out application. So we all of a sudden got pulled into these type of designs because of the fact that the distance between let's say the GPUs, if they would get more than this shorter distance, would have to be done optically. And then how do you manage that? And that's really big. So one thing we did, I guess a year and a half ago now in 2018, we got a major support from Government of Canada to develop an ecosystem and manufacturing capability to build these co-package optics. So it's good that we have it here so I can show you what you saw in our announcement is actually a
Yeah.
real thing. It's not just it's not photoshopped. So just very quickly to go through the Odin platform, so you see we got pulled into this low latency, like 0.4 nanosecond. It was measured by 5 of our customers. We gave them our qualified product, and they measured the latency to see if the protocols like PCIe or other protocols could go through our optical link without impacting the protocol itself. So as soon as you do that, let's say you have a PCIe connectivity between a GPU and a memory, or a GPU and another GPU, and they're in the same board, that's not a problem. But as soon as you want to take it to another board, then you need to make sure that protocol is maintained over this optical link. And if you have any delays changing that protocol from electrical to the optical in the physical layer, then you wouldn't be able to do this scale out of the GPUs. So it was a very interesting set of tests we did early last year, with big players in this space, and that's where we developed this concept of having an analog monolithic chip, which is drivers and all that. Yeah.
You mentioned the GPU players a couple of times. Are their requirements different than the traditional networking guys?
They are different. They're looking for for networking people. They provide the pipes, but the GPU folks are really doing all the access to memory. It's almost like it's a very different latency sensitive. There's a battle between their protocols, which are faster than Ethernet. So
PCIe.
Exactly. Like, do we do a PCIe switch? There's a couple of companies who are doing PCIe switch. You have seen already; these are publicly announced. NVIDIA with NVLink switch,
right?
NVLink. So there's a lot of debate at that level when you're trying to scale out and make the compute more effective for machine learning and AI. What networking infrastructure should you use? Do you use Ethernet, or should you use some other protocol that they already have established? CXL. There's other things as well. Yeah.
But for those guys, for the GPU type applications, is it strictly co-packaged? That's the way of going, or is a module still feasible at all?
Yeah, module is not feasible because there's not enough space. This is really and co-packaging could be of the nature of onboard optics. Or it could be jointly packaged with a chip, depending on density of what you're trying to get out. If you're trying to get a terabyte out, terabyte per second, or 2 terabytes per second out, then you might want to co-package it. If you want to get 800 gig out, maybe it's a little bit easier to attach the laser. Like you see, Odin has 2 options. One is the laser is attached to silicon photonics for lower capacities, let's say 800 gig or so. But for terabit applications, then we have the laser outside, which is what we showed you. That was a terabit application. So looking at options there are different bit rates. We've already validated all these bit rates that you see here. This is all qualified. It's not something at OFC. We're going to demo an 800 gig solution. We had all the test equipment, everything else to show you guys how we're doing that with 100 gig per lambda. So there's a very good session we had set up there. So we're doing that with our customers remotely right now. You can have PR or FR configuration and different module types, and you can also apply to different switch types. The client side of this could be anything. It could be 100 gig, it could be 50 gig or 25 gig NRZ, and it wouldn't really make any difference for us. We can scale that.
Okay.
So this is the module version application, which has Odin 8. Combined with a PAM4 ASSP, and then this module would. So you can see in the bottom here, this is the optical engine that has a PAM4 chip and our Odin platform co-packaged. So this is the first instance of co-packaged optics, but it is used in the module. So the modules will actually demonstrate all the critical aspects or roadmap from the module. It demonstrates all the critical aspects of co-packaged optics, which is fiber attach, laser attach, co-packaging on the same substrate. And if you look at the rest of the module, it's pretty empty. And that's our 800 gig module. And just looking at explosion diagram of it, it's a little bit of, this is the entire optical engine, the Odin 8 plus a PAM4. This is one variance of it. Yeah. And have other variances from there. For the
So
co-package, sorry,
just
go
a
ahead.
quick question on that one. If you could talk a little bit about the manufacturability and the yield, which
Mhm.
is
Yeah.
been a problem for so many other people.
Absolutely. So we are doing we're doing it in a monolithic process. So our high-speed driver TIAs and our silicon photonics is on the same is the same chip. There's no wire bonding. If you look at other people, they're doing a driver in one chip, TIA in another. Maybe they have a control chip in another. These are all wire bonded together, and we have the silicon photonics and maybe the laser outside. And manufacturability, a lot of it comes from that aspect.
Okay.
We also have a qualified fiber attach process, automated fiber attach process we've developed with our CM. So we actually we developed the entire piece. A lot of the weight is taken by doing a monolithic.
Okay.
That's really where most of it goes. And if you look at the co-package, the diagram doesn't look that different. This is the Odin 32. There's an electronic die to have an XSR interface to a switch chip that would have an XSR. This is based on publicly published information from two of the Web 2.0s that are doing this, and they're proposing this type of applications. And if you look at this part of it, the Odin 32 is more of the same. It's 32 drivers instead of 8. 32 TIAs, and it is the ring resonators and control chip. The laser is taken out. So that's a remote laser source or external laser source, and that gets coupled in, and then these are FR4 connections. So the chiplets I showed you, that box is really, these are the 3.2 terabit versions of this around the switch chip. Now, yeah, so that really represents the Odin 32, but the building blocks are all identical. So when somebody tests our module, are already getting familiar with how the co-package would work, because you can take this off. You can take this spring, and let me see if I can do it in real time for you. You can take this spring out and take this chip out.
Okay.
I'll put it back afterwards, but it's right. So you see, it is. This is designed for pluggability, and that's really a big feature for co-package optics. We've been doing the design development with the customers, and I think that's one of the big elements that everybody has been asking for.
And so that design, the Ethernet switching chip would be at the center of that, right?
That's correct. It'll be the 51.2T or 25.6T. This is for 51.2T, and it's a co-package. These are, as you saw, they're all spring-boarded. So these are the clips that keeps them in play. So we made a partnership announcement around this with IBM, TE, and also Senko as our partners to develop this technology. And they're all fiber connectorized. So it's these fibers go to the middle. So that's
could you talk briefly about what the other players there would be contributing, TE and Senko and IBM?
Sure. Most of it is captured in the announcement, so you can read have the specific sections. But IBM does our packaging for fiber attach, and the packaging you see here. TE Connectivity works on the connector side. Of course, they're world renowned in that space, and Senko on the connector sides as well. So there's a combination of things. I mean, if you look at the announcement, you'll have it in more detail on all their technologies that they're trying to bring into the market. And what we're trying to do also is create an ecosystem whereby this could be offered to other people, because we don't want to be the one place for everything. And our initiatives that we've had with Kobo over the past several years and other places has been always to try to figure out, well, if there's a community, we can have a quiet zone to do our innovation inside it, where the interfaces are the same. So there's a footprint here. There's a spec on the optics. There's a spec on electronics. Inside there, people could use different technologies. And our technologies are patent protected, so we don't really mind. It's anybody who wants to do it, whatever they do. And we see the specs that are coming out. They are significantly higher power consumption than what we can achieve. So we know to some extent the companies are trying to find a spec that that can hold many people in it. So some people might have a more technology, power intensive or type of solutions. And as long as we can agree on the physical dimensions of it, or maybe the entire board is the the common interface, or maybe XSR is the interface here, and then the fiber is standardized with DR and FR. Maybe we standards on the connectors here to the board, or something that and the physical dimension of it, like we did with Kobo. I think the industry has to work that, but we are building the core technology that could be, the tires of it could be kicked in a module simultaneously with this. So if somebody wants to choose a module track, well, they can take that.
Do you have to build more partnerships out there, especially with the Broadcoms and Barefoot and the other switching players?
I think we don't really need to, unless we want to do something proprietary. Let's say if Broadcom is interested in doing something proprietary, then yeah, we could do a partnership to build something for them using our engine inside their chip to get them ahead of everybody else. I think we're looking at those things as more opportunistic. If somebody's interested, we have the technology that is differentiated and is patent protected, and we have demonstrated our power consumption and costs with our current design. So there's really little technology risk left, to take out of the system. But in most cases, we rather work with people that we can create an ecosystem, and because let's say with hyperscalers, they may want to buy the chiplets themselves. If you think about it, they may buy the chiplets, and they might want to have their CM build this substrate here, and then buy the chiplets from us or from somebody else, and that substrate might have a Broadcom chip here, or or other people's chips. The credible ones would be, I guess, the other chip vendors that are in the market. Yeah.